Hello, everybody, and this is Bugsy Codes. Okay, Bugsy Codes. This is the first video of my channel, and welcome to this video. And today I'm going to be explaining Krushkal's algorithm. So first off, who is Krushkal? So Krushkal is basically this man. His also full name is basically Joseph Krushkal. Okay, in case you wanted to know. Anyways, he was born in 1928, and certainly he had. He just passed away in 2010. That's sad. Well, anyways, that's something that we don't care about. What we care about is the algorithm. But anyways, as they say, great men never die. Great men die, but their ideas do not die. So in with that being said, well, let's dive into the Krushkal's algorithm. Anyways, getting into the Krushkal's algorithm, where is it exactly used? Okay, let me just tell you what Krushkal's algorithm is designed for. Let's say you are at at point A, and there is another area. Let's say point B over here. Okay. Hmm. Okay, fine. Point B and point C over here somewhere, and let's say point D over here. And also probably include something like point S, point W, point D, E, sorry, E. I'll just call this F instead. And G, whatever. Okay. So as you can see, they all have certain distances amongst them. Okay, this is not a straight line, right? Between A and C, it is not a straight line. So it would probably take a lot of distance. However, probably B and F is a shorter distance. Okay. So what is Krushkal's algorithm basically? So Krushkal's algorithm is basically to find a path. Okay, that's the goal. It's to find a path that would potentially cover all the nodes, the cities. Okay, let's say this is the map. This is a map of GTA. Okay, GTA 5. Okay, what is the goal? You basically have to visit all these paths. That's your goal, and you basically have to visit all these cities, and but then you have to basically all these cities, but then you have to do that in such a way that would take you the less number of path space, the least traveling distance. Yeah, that's more precise to be said. So I guess since A to C would be a really long distance, A to E was plausible. However, the distance is not so great. So I could say that A, B, sorry, what is this? F, G, D, C, E. Going in this sort of fashion basically allows you to meet all the particular nodes or cities. I'm sorry, I'm using nodes because probably you may not know, I've not heard of that. So you basically have to visit all these cities in the most optimal approach, in the most optimal, the distances. Okay, so these distances could be like A to B could be 2, and B to whatever this F is 6, blah blah blah, and stuff like that. Okay, whatever this sort of map that I just said, okay, is going to be converted into some in a data structure format called as graphs. Okay, in case if you're learning for the graphs for the very first time, I'm going to tell you that it's going to be represented in the form of edges. Okay, each edge is going to have a U node, one of the node, and another node. Both of these would be connected, and if it is a weighted graph, okay, just as it is in this case. So I would call this, I would attach a weight alongside it. So the edge would look like something U, comma V, comma W. Okay. So this is the edge of a weighted graph, like in one of these weighted graphs that I just showed. Okay. For the same thing, whatever I explained, I'm gonna show you an example. I'm sorry. Yep. Okay. That's just getting our way. Oops. Okay, so this is better, I guess. So this is our graph. Okay, Well, I really hope you can see these bunch of numbers as well. If you cannot see them, that's completely fine because I'm gonna just write them over it. 8, 1, 7, 11, 8, okay, 2, 6, okay, 4, 2, 10, 14, 9, and 7. So, based on these number of nodes and the respective distances amongst them, you could say that there would be at least many ways to basically connect these places, by touching all of these nodes. But then you basically have to find the path that would cost you the least amount of total distance that it would be traveled. Okay, I'll tell you something. Okay, this guy Krushkal basically, he basically devised in such a way that he told, according to this algorithm, he told accordingly that you basically have to form an MST and also have don't worry, I'll explain you what it is, and also in the most optimal approach. Okay, by optimal it means the least cost. Okay, so what exactly is an MSD? Okay, if in case you're confused what MSD stands for, it's basically minimum spanning tree. So what is a minimum spanning tree? So a minimum spanning tree, there could be multiple ways to basically represent this in terms of minimum spanning tree. By the way, what is a minimum spanning tree? So minimum spanning tree is a same graph that could be represented through paths that would connect all of these nodes some way or the other, okay, without actually forming a cycle in any sort of way. Okay, there should not be a cycle, and it should connect all of these nodes. Okay, so if I would go from 1 and then 0, 7, 6, 8, 2, 3, 4, and 5, that is an MSD. Okay, that would look something like this. Okay. I'll just give you another example of how the MSD should look like. I'll just tell you the answer, which for what we are actually striving for. Okay, so this is one of the MSDs. What this guy starts over here, and it goes here, it goes here, it goes here, it goes here. 2, 8, 3, and 4. It could be, split in this sort of way. You don't always have to go to a straight line. So this is an MSD as well. There is no cycle. If I were to connect these two things, if there was an edge and if I did connect them, then it would form a cycle, and this would no longer be called as an MSD. For those reasons, we are not going to connect them. So just showing you that this is an MSD that we have created. However, there would be a path sum, okay? So if I were to basically add these sort of things, since this is the answer, this is the most optimal approach. I'm not going to tell you, sorry, I'm not going to skip this sort of thing. I'm going to tell you just directly the answer, but I'm going to tell you how to basically get sort of these sort of sum as well, okay? Okay, so firstly, 4 plus 8 plus 1, which is 12, 13, 15, 19, 21, 28, and 29, 37. Okay, so that's your path sum, and this is the most optimal MST, which according to Krushkal's algorithm would be the answer. Okay, I mean, that's the most optimal approach that you could go about taking. So now the question that arises is, you know what an MST stands for and what it exactly is, and but then how do you in the world actually go about finding the most optimal approach? Okay, well that's where um, you know the weight-based sorting comes into picture. So you basically list out all the edges, and these are the edges u v. Okay, this is u, this is v, this is the sender node, this is the receiving node, and this is the weight of that particular edge. Okay, so 7 to 6. Okay, I'll just draw this diagrammatically just so that you understand. 7 to 6, and the weight of this is 1. Okay, this is the node, and just so that you get to see how the graph looks like, 7 to 1, and the weight of it is 1. I'm so sorry, did I mark it as 11? Um, Oh, I'm sorry. 7 to 6 is one. This one, okay? 7 to 6 is one, and the weight, the corresponding weight is one. So as you can see, I've listed all of these. You basically have to basically list all of these edges and then perform sorting operation not based on their source nor on their destination, but rather on the weight. Okay, with the rest of by weight we actually mean distance. Okay, distances. You see, Krushkal's algorithm is basically used in various forms, okay, various methods. You might ask, where in the world would I actually use Krushkal's algorithm? Where would I have to use the shortest path? Okay, let's say you basically have to travel all these nodes and also reach up over here, and then you basically have to go from here to here, right? In the shortest distance as possible, covering the shortest distance. So you would basically have to go about using Krushkal's algorithm. Let's say you basically have to create a pipeline-like structure where you basically you basically have to connect all these particular cities. And what is the shortest distance, the shortest pipeline infrastructure that you would require? That would be the distance of this, right? And that is where one of the places where you can actually use. It's also used in neural networks, computer science, other parts of computer science. We're not going to talk about that for now. So now that you've understood what MSD is, that's something looks like this, which basically touches all the vertices. Okay, may not, and it would not form a cycle. It just so it touches all the vertices. It could be called as a minimum spanning tree, and it will not form a cycle. That's one thing you could, you know what an MSD is, and now you know that for using an optimal approach, that we're going to basically sort it in terms of the weight. Okay. And also, there is another thing that we have to learn now that we're going to learn about this. So, the weight, right? We're going to basically optimize this in terms of weight. So, we have all these edges that we have listed up across from this sort of thing, and we basically listed it and then also sorted it. See, as you can see, the weights are sorted accordingly: 1 2 2 2 4 4 6 7 7 8, something like that. So it's sorted. Okay, now, is our life sorted? That is not something we are sure of. So for those reasons, we will basically take the very smallest weighing edge, or in simple terms, should I say, the shortest distance edge. Okay, I'm just gonna write that 7, and then I have 6, and the weight of this, or the distance cover that it covers, is basically just one unit. It could be a kilometer, it could be a meter, whatever you would like to call it as to be. Okay, and the next up in our list is 822, and with a weight of 2. So this guy is out, and now this guy is out as well. Okay, so we have 2, and then we also have, sorry, 8 comma 2. Sorry, we have 8 and also 2. So as you can see, these two things are not connected. Okay, there's something that you have to know in the next process that is going to happen, which is 2 to 6, right? Sorry, 6 to 5. So as you can notice that, this is something very important to notice, by the way. As you can see, 76 was already created, and now you're going to create 6 to 5, right? 6 to 5. 6 was already used, and now you're going to use 6 to 5. So basically you have to connect them in such a way. Okay, um again, you can still connect them, there wouldn't be a problem. Well, okay, there wouldn't be a problem. Well, the problem would arise when you are in a situation something like this. Okay, I think you guys have understood what I'm trying to say. You basically take this out as well, and then basically connect that again, and you can connect this as well, and connect this as well, and you can connect that as well. Okay, okay. So what the problem would arise is, suppose, okay, you're over here, and the next edge in the top of your, what do you say, the less weight thing, Let's say you have 8 to 5. Okay. I just Okay, wait. I think that is okay. Fine, fine. Okay, listen. So add edge 2 to 3 in MST at this particular point, as 8,6 cannot be added. Okay, I'll tell you where exactly we are standing. We have covered all these edges. Make a note down with your pen and paper. Maybe just draw it, okay, through all these, particular source and destination and the respective weights, and then basically try to figure these things out till here. And after that, 6 to 8, 6 to 8. These two things cannot be connected. And why is that? These two things cannot be connected because it forms cycle. Okay. And now the question is, how in the world would you tell a computer that this sort of path would actually lead you to creating a cycle? Okay, how do you do that? So, and this is where the concept of disjoint sets come into picture. Disjoint sets. Okay, so disjoint sets come into picture. Um, so you're over here. You can't add uh, you can't add 8,6 as it says 8,6. Also, shout out to Geeks for Geeks for these images that I've just got. They're not sponsoring me, by the way. This is my very first video, so 8,6 cannot be added. Why? Because it forms a cycle. How are you going to tell this to the computer? Okay, how are you going to do? So, how am I going to even resolve it using disjoint sets? Okay, concept of disjoint sets. Okay, let me tell you something. Okay, if I were to tell you, if I could basically add anything from this to this, you could say yes, I can add it anywhere I wanted. It would never form a cycle at all. So, right, that wouldn't form a cycle. But however, if I were to add something from this to this, it would form a cycle. Even from this to this would form a cycle. From this to this would form a cycle. So if you were to notice something, these two nodes are basically connected directly or indirectly. They're connected, 8, 2, 5, 6. Okay. And 6, 5, 2, 8. They're connected. 6 and 8 somehow they have some blood relations that just cannot be expressed properly. So they are connected. So this is where disjoint sets come into picture. Okay. You basically are going to see if they are connected or not. If they are connected, that means they share the same parents. Okay. So how does disjoint sets help you? Okay. So there is something, a concept of having a parent, a common parent. Okay. Let's say uh, 7, 6. So when it's joined, 6 has to be told, I mean, 6 has to be represented in such a way that its parent is basically 7, right? 6 parent is basically 7, okay? Well, 7 is the parent himself, so his parent would be the parent, I mean, him himself in the 7 itself, okay? So, when I'm also adding 5, when I'm adding 5 over here, what's going to happen is 6's parent also happens to be 5's parent. Okay, so who's 6 parents now? 6 parent is basically 7 and the 7. Okay, now 7 also happens to be 5's parent. So when you basically try to link through stuff, and when they share a same parent, we can say that they are connected component. Okay, I'll tell you. And how do you basically represent this in coding point of view? Okay. Okay. So now you have parent list. Okay. This is a parent list. You can create a set, list, whatever you want. Okay. I'm going to create these as such that they would be the parent of the vertices themselves. Let's say I create, I'm so sorry. It's created a lot of these structures. Okay. 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 So if I were to create a node, say 0, so I'm saying that zero's parent is the node itself. Okay, this is just for our understanding, but it just it's more like saying that the zero doesn't really have any parent, at least as of now. Okay, um, okay. Zero doesn't really have any parent at this point. Okay, so yeah, I think I can represent this over here. So 0 and 1. Okay, so 0 and 1. So the parent of 0 is the node itself, which is 0. For 1, it's the number itself, which is 1. And for 2 and 3, it's going to be the same. Okay, this is what the initial state looks like. I'll tell you exactly. Okay, this is not connected, by the way. These two nodes are not connected. They just are existing and they are disconnected. And I'm going to connect them. Okay, 0 and 1. Now they are connected. Now that they're connected, I'm going to tell that 0 is going to be 1's parent as well. So instead of this index 1 2 3, at this particular index, I'm going to mark this to be 0. So that means now that 1's parent basically is 0. So if I were to do p of 1, which is this particular index, I would basically get 0. So I would get the parent of 1 to be 0. And now if I were to basically also connect 2 over here, and also I'm going to basically say 0 is 2's parent. 0 is 2's parent. So I'm going to mark this to be 0 as well. So you might be like, yo, what if I basically added 2 over here? How are you going to tell that 1 and 2 are connected to each other? So how am I going to tell if they share the same parent? Because the way that I'm going to say if they're connected is basically if they share the same parent, right? So 1 and 2, they connected. I'm going to check what is the parent of 1. Okay, 1's parent is 0 and 1's parent is 0. So P of 1 is equal to 0. So 1's parent is 0 and P's, 2's parent is going to be parent of 1, which is going to be 0 again. So this is going to be set 0 as well. So all of these three, including 0, 1, and 2, now they share the same parent, which is 0. Okay, this guy shares the node 0 itself. So in that sort of way, we can basically represent that they belong to the same connected component. They basically share the same parent. Okay, I think with all of these screamings, I really hope you guys have understood what I'm trying to say. Okay, trying to say. But then there is okay, how do you basically make the computer understand exactly? We'll cover that sort of thing later on in this video when I'm going to type in the code. So I really hope the concept of parents were understood. Okay, now I'm going to explain with a bigger example. So now you have 7, 6. So 6 came into picture and then you added 5. So 5 came into picture and then you added 2 and then you added 8. So all of these sort of things basically came into picture. So okay, now let's say if you have basically added two different components. Let's say you had these three and you also had these two. Okay, so when I basically connect these two, let's say initially it was something like 7 was owning 6 and 5. Okay, and 2 was basically owning 8. Okay, 2 was basically owning 8. So what happens over here is 2's parent basically happens to be now 7. Okay, so they're connected in this sort of way. But if there is some sort of so if I were to find 8's parent, I'm going to find out until I find a node that is the parent of the node itself. So I really hope you've understood what has happened over here. So these two were connected and these two were connected as well. And as soon as I connected 2 to 5, 2 to 5, 5's parent is 7. So 2 basically represented its parent, P of 2 to be 7. But however, P of 8 is basically 2. So if I were to find the parent of 8, it should give me 7 because all of these should give me the same result. Okay, I really hope you're understanding what I'm trying to say. So 7, 6, 5, 2, and 8. Okay, so how is 8 going to tell me that it also belongs to 7? Okay, so the way it is done is it's going to recursively call its parent as long as it finds an ancestor who is the parent of himself. He's probably asexual, probably a chicken or an egg, I don't know, but he is a parent, and he is the ultimate parent that basically withholds all the connections of that connected component. Okay, I'm just trying to make some jokes, but don't take that too seriously, whatever. And I blabber sometimes. So with that being said, I really hope you guys have understood what I meant to say. You basically connect these two things. 8 to 6 cannot be added, and you basically add 2 to 3 at this point. Instead, go for the next one. 8 to 6 cannot be added, and you add 2 to 3 and things like that, and then all of these things would be done, and finally you would get an MST, and there would be some bunch of remaining edges which you probably would not want to mess up with. Okay, you don't really need them, they're no longer in use. So these edges are enough for us to basically complete these MST, and also in the most optimal way. Oh, okay, so with that being said, now let's get into the coding part of Krushkal's algorithm. Okay, I'm not going to type this code, I'm just going to explain completely. So in Python it's different. Okay, there's certain different ways you can actually go about solving this question. Just so that you guys understand, with the same rated graph, I've basically drawn the same graph, and it has given me 8 to 2, right? 8 to 2 with 2, 0 to 1. Okay, it's actually supposed to be, by the way, because it's a undirected graph. I have to draw it. Yeah, now this serves it well. So there's a connection between 8 to 2 and 2 to 5, 0 to 1, and all of these. Okay, it's basically the same answer for the same bunch of nodes and vertices that I've given. Okay, let me just explain how this sort of thing basically works. So you might as well want to take a break for now and then come back to watch this part of the lecture. Okay, so assuming took a break and now you're gonna relax and enjoy. So what is graph? As I said, a graph is a data structure. Usually it's represented in the form of edges in the format of UVW. Okay. There's several different ways you can actually represent them. One of them would be adjacency matrix, adjacency list, whatever you'd like to call this to be. Okay. So I'm going to initialize the number of vertices. This is an initialization of the graph itself. And I'm going to pass in the number of vertices my graph is going to take. Okay. I'm sorry. Uh, I'm gonna basically pass in the vertices array of lists. Python is different, built different, totally. So this is, and as soon as you do self.v and is equal to v, it basically interprets to be a integer array data type. So self.v happens to be equal to v, and self.edges would be equal to this. Okay. As soon as it basically is started, you basically have a total number of vertices in it, and you have an empty adjacency. Sorry, this is the edges, by the way. Okay, edges, and this is the adjacency matrix. So I really hope you know what an adjacency matrix is. I really don't want to have to explain to you. So I is to array for I in V. Okay, adjacency matrix. So let's say it is for index 0, and what are the vertices that it basically protrudes towards. So let's say for 0 it basically protrudes to 1, and what is the weight it corresponds to? Maybe 2 is the weight, and next and this would be in the list, so you can basically add that sort of thing. um, and then you can basically add 3 and the weight it basically corresponds to, and things like that. Okay, so all of these things would be in this sort of fashion. This is just an indexed version of it, 0. Okay, so it would be like this would be completely like an index, 3 comma, let's say 2. Okay, this would be just one of these indices, right? I don't want to explain this thing in depth. So next step is adding the edges to it. Edges to it. Whatever edge you have, you're basically going to append U, V, and W. U is the source, this is the destination, this is the W, and this is the adjacency matrix that we are talking about. As I said, we're going to index this to the source and basically append the corresponding destination along with its weight. Again, since this is a undirected graph, we basically have to add with respect to the destination to the source with the corresponding with the same weight. Okay, so if you're saying Delhi to Mumbai is equal to Delhi to Mumbai is basically 5 kilometers, and you have to tell that Mumbai to Delhi is also 5 kilometers, right? With that being said, with that being said, you know, it's an undirected graph, and self dot adjacent edges dot append. So you're basically adding the edge in this sort of function. That's it. Basically adding the edges over here. You're basically adding the updating the adjacency matrix. Okay. And the next step is FUP. What does FUP stand for? FUP, I mean, you can basically name it however you want. So FUP, by what I mean by it is find ultimate parent of whatever you're trying to find, so the self is a very important thing to put in, so that you are addressing the graph that you are basically you're trying to address. And next you have p, which is a parent array, as I explained it earlier in this video, this one. Okay, and I did explain you about this guy, this sort of problem that you could actually go about facing. So the node has to be the parent of itself. Okay. So for 7, is the parent of 7 equal to 7? Yes. That means I basically have to return 7. So that's the answer. As simple as that. And for 6, what's the parent of 7? Sorry, is 6 the parent of itself? No. So I'm going to use its parent. I'm going to return the function for its parent. 6's parent is 7. It is going to be recursively called, and 7 is the parent of itself. So it's going to get stopped, and for 6, it's going to return 7. And for 8, it's going to check for its parent. It's going to check if 8 is a parent of itself. No. It's going to check if, of its parent, which is 2. Is it a parent of itself? No. Then you go further. Is this guy a parent of itself? Yes. And that's how you release, sorry, you basically go about returning 7. Okay. And that part. Okay. So they had I had to make a little bit of change in the code. So this is the rank of ultimate parent of U is greater than the rank of the ultimate parent of we. Well, in that case, the parent of ultimate parent of we should also be should now become the child of UPU. That means UPU is now the parent of UPV. So that is how it basically is. Okay. So if I had, if one of these nodes, let's say 1, and I had another one, which is 2, okay, I'm going to check as I said before, the rank of both of these numbers, initially, the nodes would be equal to 1, okay? So Since they're equal, I would have to increase any one of these. It's going to be random, whichever happens to be you. I could, change this sort of thing to be another thing as well. So this sort of thing now happens to, okay, well, now this sort of thing happens to be the parent of UPV, right? So what that means now that I have to increase the rank of UPV, right? And run the same code. I really hope that gives you the same. So UPV. So now the rank of uh, 2 is increased to 2, and the rank of 1 is 1. If I were to see this in a sort of array, let's say 1, 2, okay, wait, 1, 1, okay, 0, 1, 2, 3. Now, if I were to just basically go about adding another node, which would be 3, so its parent has a rank of 2, which is greater, so that means 3 gets submissive at this point and basically happens to become two's child. So the rank remains the same. Just that three happens to, this is the parent array, by the way, now at this point. Now, three basically happens to become the parent of, um, sorry, the child, sorry, three basically. So for 0, it's 0 itself, and for 1, it is basically 2. 2 is a parent. Okay, when things are same, it basically can be anything, and the rank of 2 has been increased. And for two's parent, it is basically 2, and for three's parent, it is also 2. So now with this being said, we can just say that all of these three things basically belong to the same component because they have same parent. Okay, same component because they have the same parent. Okay, so with that being said, if the rank of any of these parents is basically equal, so this guy happens to be the parent now. UPV is greater, so UPV happens to be the parent of UPU. It's saying my rank is greater, so it's going to increase. But since they're equal at certain point at else condition, so we're going to have to increase randomly at one of those things. We have to increase the rank of it so that there wouldn't be a clash. Okay. With that being said, let's actually get into the code part of it. Self MST, which is you can create set list or whatever you want. Okay. And now you have the parent set, and you also have the rank set as well. And for I in self dot we, okay, as long as many vertices you have, you basically have to initialize parent to be the node itself. So the node 0 is going to be the parent of 0 itself, 1 is going to be parent of 1 itself, and things like that. Okay, as I explained it before, I really hope I don't know how to explain it again. So it'll become 0, 1, 2, and 3. And the rank would be 1, 1, 1, 1. Okay? So the rank would be 1 initially. And I'm going to sort these edges according to which is x of 2, which means the third component, which is basically w. Okay? This part of thing. Okay, so once they're done sorted, and I'm gonna basically iterate through the edges in the sorted edge and basically extract u, v, and w and find their ultimate parents of u, find the ultimate parent of v. Okay, and basically if their parents basically are not connected, that means there are like something like this. Yeah, so there's something like this. At this particular step, you want to add 2 and 5. So as you can see, 2 and this sort of thing, this component and this component is not connected. because this guy's parent is basically 2 and this guy's parent is basically, let's say, 7. Okay, so these two are not connected because their parent isn't the same. Okay, that is how you find it out. And now you're going to basically add this to your MSD, because you're basically joining all these edges, and also you're going to create a union. Okay, when you perform union operation, it is going to form a connection. By forming connection, it also updates, you know connection, it also updates same parent, same connected component, same parent. So one of these things will basically have the same parent. It could be 2, it could be 7, who knows? It all depends on the code. How the code functions. So now they're connected. So things just cannot be connected over here because 8 and 6 basically happen to share the same parent over here. So 8 and 6 basically have the same parent. So they cannot just be connected just like that. So um, it's going to be added to the edge, and then performed in union. And if they were equal, that means it's connected. So you're not going to do anything. So, and finally, you can return MSD. Okay. You basically add the vertices here and basically have all these edges uh listed across, and add all these edges, basically, and sell MSD, sell g.Krushkal. You basically return the MSD. So yeah, I'm gonna print the MSD. So as I said, it's the same shit. So 8 to 2, 0 1, 76, 3 to 4, and things like that. So this is an MSD. I really hope you guys have enjoyed this video. Um, Took me a little while. I was a little energy drained. I'm so sorry. This is my very first video. I really hope you enjoyed. If you enjoyed, just like, share, and subscribe, and leave a comment or feed.